Hello everyone and welcome to Unit 5, Day 4. We're going to be talking about quadratic formula. We've already done the first page of it, or most of it at least, and so we're going to start right on the discriminant. And just as a reminder for you guys of what the quadratic formula is, remember we said that's x equals negative b plus or minus the square root of b squared minus 4ac all over, that's not good, all over 2a. The discriminant portion is what's inside the radical. And we know that if inside the radical is a negative number, which means it's less than 0, so we'll go right down here, less than 0, we know that the roots do not exist. If the roots do not exist, we then can say that these are imaginary roots. And to be specific, we're going to have two complex roots. And we'll get into that later on. A picture of this is if there are no real roots, because we call them imaginary, then we can have two different examples of what a quadratic could look like. You could have one above the x-axis, and it looked like that, or one below the x-axis and look like this. They never touch the x-axis. That's the key, that if the discriminant is less than 0, they're imaginary and they never touch the x-axis. The next example we're going to do is we're going to look at when the discriminant equals 0, which means inside the square root is equal to 0. Let's make up a number. Let's make up x equals negative 4 plus or minus the square root of 0 over 2. Well, we are then not adding and subtracting, we're just getting x to equal negative 2. And therefore, we are going to have how many roots? Just one. So we're going to have one real root. Now, the key here is that if it's one real root, we know that a quadratic always has two, quote, two roots. So here we're going to have a double root. And if we remember back, a double root, or of double multiplicity, maybe we should say, double multiplicity meant that it touched in turn. So it's going to look like this. It's going to hit the x-axis and turn around. And here's a better picture of it. So again, it's double root or multiplicity. It would be maybe something that could look like y equals x minus 4 squared. And it's that double multiplicity there. The last one is if the discriminant is greater than 0. Now we could get an example here of x equals 4 plus or minus the square root of 16 over 1. And in this case you're going to get 4 plus 4 over 1 and 4 minus 4 over 1. These are nice roots, and that's because it's a perfect square. The discriminant inside was 16. It's a perfect square, so these are going to be two rational roots. And the sketch could look something like this. Two rational roots. You get here and here are your roots, and so good to go. The key is that they're rational. If it's not a perfect square, in the last example we'll do here, and it's over to the side here, but you could do x equals 2 plus or minus the square root of 5 over 1. Those are not going to be nice, so we're going to get two irrational roots. Not that they're not going to be nice, but they're not going to be perfect, nice perfect decimals for us, so we're going to get irrational roots. There's no difference in what that graph is going to look like or what it could look like. It's the same idea. It's just that they're not nice perfect numbers, they're irrational numbers. So that's what a discriminant tells you. It tells you whether there's 2, 1, or 0 roots. And if the discriminant is a perfect square, it tells you that you have two rational roots. And if it's not a perfect square, that they're irrational roots. And hopefully that makes sense using the quadratic formula. So to finish, we're here with two examples. Calculate the discriminant. The discriminant is b squared minus 4ac. It's what's underneath the radical. A, B, C. So I'm going to get 5, negative 5, it doesn't matter though because it's squared, minus 4 times 2 times negative 2. So I'm going to get 25 plus 16 gives you 41. It's a positive number, so I know the roots exist, and it's not a perfect square. And so therefore we have two irrational roots. The next one takes a little more thought. It's asking you to find the value of k, because we know that the b is the k. So what must the values of k be to have exactly one root? Well, we know that the discriminant must equal 0 to have one root. So therefore I plug in k squared minus 4 times 9 times 4 equals 0. K squared minus 36 times 144 equals 0. And now notice there's two ways to solve this. You have a binomial that's a difference of two perfect squares, so I could go k plus 12, k minus 12 equals 0, and get k to equal negative 12 and k to equal 12. Or the other way I could have done it is set k squared equal to 144, and when you square root, the key thing to remember is that k equals plus or minus 12. A lot of people forget the plus and minus, and that's why I sometimes like doing the difference of two perfect squares. But you get plus or minus 12. And either way, that will give you one root. K can be 12, or k could be negative 12. So that's what the discriminant is. So the next page is working on more examples. So I'm going to do the first one for you, take a break, you guys do the second one, and come back and we'll see how it went. So the first one, it has to always be set equal to 0. So remember that's 8n squared minus 4n minus 18 has to equal 0. One thing here that you could see is you could divide everything by 2. You don't have to, but I could to make it more simple. I'm not going to, and I'll show you how it works in the end here. So A is 8, B is negative 4, C is negative 18. So if I wanted to write those out, I'm going to get n, it's not an x this time, n equals 4 plus or minus the square root of negative 4 squared minus 4 times 8 times negative 18 all over 2 times 8. I'm going to continue this. 4 plus or minus the square root of 16 minus 4 times 8 times negative 18. Let me go get my calculator. So you get plus 576 all over 16. Keep going, n equals 4 plus or minus the square root of 592 over 16. So you sit here and you go, okay, I got to this point, now we need to simplify. So this is where we go, what perfect squares go into 592? So getting our perfect squares at the top here, I figured out that 592 went into 16 the most amount of times. So you're going to get n equals 4 plus or minus the square root of 16 and the square root of 37. Now, we're going to continue to go across here, and sorry for those of you if you want to write smaller. We're going to get 4 plus or minus 4 square roots of 37 over 16. This is what I need to show you, is here, notice that each part, and this is going to be key, you have that part and you have this part. They're separated. So we need to get n equals 4 divided by 16 is 1/4 plus or minus another 1/4 square root of 37. The 4 and the 16 can be simplified, and then the 4 and the 16 over here can be simplified. You cannot sit here and simplify anything in the square root of 37. Okay, that's key. So this is your final answer, and I like to split it up just so you can see that it's two separate things. Why don't you guys try this top one here, and I'll come back with the answer. So pause it and try it. And so here is the answer to the second one. Let me give you an arrow that points to it right there. You can see all my work. The key that I wanted to show you was right here. You should have had 6 divided by 18 plus or minus 4 square roots of 27 over 18. You can do 6 divided by 18. Notice they're both divisible by 6 and get 1/3. With 4 and 18, though, they're not divisible by 6. They're each divisible by 2, so you're going to get 2 square roots of 27 divided by 9. So your final answer is 1/3 plus or minus 2 square roots of 27 over 9. And that's your answer. You do not, notice that they don't simplify necessarily the same fraction. If you would like to try the next two, you're more than welcome to. If you pause it, I will put the answers up there. If not, I'm going to go over the final 2 problems. So pause it right now if you want to see the answers. So there are the answers to the middle 2. And moving on to the final 2. If you look at these, they look difficult, and all we need to do is find a common denominator. And that's the key. One thing here with the first one, notice that you can factor that. So our common denominator is actually x times x minus 5, which means I don't need to multiply anything to the first term. I do need to multiply x minus 5 to the second term, and I need to multiply the last term by both x times x minus 5. What I would like you to do right now is pause it and do the entire numerator portion of it, set it equal to 0. What I will tell you is that due to the denominators being the same, they will, you only have to worry about the numerator. So the denominator you do not need to worry about as long as you have common denominators. So please do the top, set it equal to 0, factor, and solve it, and I'll come back with the answer. If you got stuck right here, this is double distributing, so please make sure to go do that. Pause it again. I don't want you guys to cheat and go right into it. Simplify this, set equal to 0, factor, and solve. You'll notice that you didn't have to factor. The x squares canceled out, so you're good to go, and you should get in 36 over 7. Try the next one. I'll give you a hint halfway through if you get stuck. Hopefully you got the common denominator to be n cubed plus 5n squared, which can also be factored into n squared times n plus 5. That's really how you know you get that. So I already had written here what I multiplied each of the terms by, or the fractions by. Now that the denominators are all the same, you can only worry about the numerators. So take the numerators, set equal to 0, factor, and solve, and this time, yes, you will need to factor. So hopefully you got 0 and negative 1/4. The reality, though, is that you have to check because it's a fraction. And when I plug in 0 into the denominator here, I'm going to get 1 over 0, which makes this undefined. And I can't have that. So therefore, I will cross off that answer and only get negative 1/4. See you in class.